Hello everyone, welcome to this lecture. In the last lecture, we have discussed crystal field splitting in octahedral complex. Then come to tetrahedral complex. Okay, this difference in geometry. Okay, in this case, coordination number is 4. Metal ion present at the center, but ligands are present at the alternate corner. If you represent it at this cuboid, then it will present at the alternate corner, and these ligands are present in between on the axis. These are present not along the axis but the in between the axis. Ligand of this geometrical position are present in between the axis, not on the axis. None of the ligand approach to the metal ion along the axis, but between the axis. Hence, when the ligand approach, the repulsion of electron present in this non-axial d orbital, that is dxy, dyz and dxz, which are oriented between coordinate axes, experience more repulsion. In this case, the repulsion in non-axial orbital and electrons present in non-axial orbitals and this ligand will be more than the electrons present in axial orbital and ligand. And as a result, the splitting of these 5d orbitals occurs in different way. In this splitting, the axial orbitals having lower energy after splitting, this non-axial orbitals goes to higher energy, and in this case also splitting takes place, that is called tetrahedral splitting. And in this case, these 5 degenerated orbitals split into E and T2. Okay, these two are E orbital. In this case, axial orbitals are called E orbitals. Okay, and non-axial orbital are called T2 orbitals, and these are present at higher energy after splitting. These orbitals are present, that is dz square, the x square minus y square present at the lower energy. Okay, this is the presentation of this. Represent the free metal ion of d orbital. This one is generate d orbital of higher energy. This one is crystal field splitting in tetrahedral complex. This 5d orbital, degenerated orbital, splits into 2, that is E orbital and T2 orbital. Non-axial orbital present at higher level, axial orbital present at the lower level, and this one is very centered. In this case, this is the crystal field splitting energy, which is denoted by del T, T for tetrahedral, okay, or 10dq. Okay, and this lowering of E orbital done by this amount of energy, that is 0.6 del T, and increase in energy of this T2 orbital is done by this 0.4 del T. The difference will be del T. This difference will be 1.6 del T. This difference will be 0.4 del T. We have discussed all of these facts in this octahedral. It is the similar splitting but in reverse order. In this case, axial orbitals are present here and non-axial present here. Okay, this is the metal ion, free metal ion d orbital. These are the d orbitals at higher energy in the presence of spherical ligand field, and this is the splitting in tetrahedral geometry. Okay, it is the representation of tetrahedral complex splitting. This crystal field splitting energy is denoted by del T. In this splitting, energy of T2 will be higher than energy of E. E is axial orbital, T2 are non-axial orbitals, E orbitals are axial orbitals. Okay, dxy, dyz, dxz are the T2 orbital, and dz square, dx square minus y square are the E orbital. This is the similar splitting but in reverse order, and in this case, this del T will be always smaller than del O. This crystal field splitting energy will be always higher for this octahedral than tetrahedral. The low value for the crystal field splitting energy for any octahedral complex will be always higher than the tetrahedral complex. It is due to presence of less number of ligand in tetrahedral complex. There will be only 4 ligand. Presence of only 4 ligand in tetrahedral complex, and this crystal field splitting in this case will be lower. Okay, and it is the ratio, that is this del T will be minus 4 by 9 del O. It will be equal to the 4 by 9 del O. It is less amount than this del O. That is 4 by 9 del O, and this negative sign shows the reverse splitting. You can also write this delta is equal to 4 by 9 del O, but negative sign shows the reverse splitting. It means the axial orbital goes to lower energy and high T2 orbital, non-axial orbital goes to higher energy level. Okay, then come to distribution. It is similar. All the tetrahedral in this case, the distribution of electron in d orbital, in this case all tetrahedral complex form high spin complex. Low spin complex possibility is nil, because this crystal field splitting, that is energy, that is del T in these complexes is small, and it will be always smaller than pairing energy. Low spin complex will be formed when this crystal field splitting energy will be higher than pairing energy. We know that, as this del T is always smaller than this pairing energy, right? So no unpaired electron is more, there is no possibility of low spin complex, and number of unpaired electron, it will be always high. It will form high spin complex, right? And we can see this distribution in this tabular form. We can calculate, in this case also we can calculate this CFSC. We can show the arrangement. For example, in the case of D1, in this case only one type of arrangement is possible, that is high spin arrangement. Pairing occurs after singly occupied 5d orbital. Okay, this first one D1 configuration will show this type of arrangement, that is E1 T2 G0. One electron goes into E1. If one electron will present only, then it will present here. If another electron present for D2, it will be present here. Then third electron will goes to this, because pairing energy will be higher than the delta. Okay, you can see this arrangement, that is E1 T2 0. Second electron E2 T2 0. Third electron will go to the will present in the T2 orbital. Fourth electron in T2 orbital. Fifth electron in T2 orbital. Okay, it means electron filling takes place in this way, that is this first electron will go in this, then this, third, fourth, fifth, then sixth, 7th, 8th, 9th, 10th. Okay, one arrangement is possible for each configuration, and we can calculate CFSC for that. We can calculate CFSC in this way. This electron present in lower level, that is E orbitals, will cause the lowering of energy by this amount, and electrons present in the T2 orbital will increase the energy by this amount. This minus sign is due to lowering of energy. Okay, and you can calculate with this formula. You can calculate for each configuration, you can calculate this one CFSC, and it will be 0 in the case of D5, it will be 0 in the case of D10. Okay, and then you can calculate spin only magnetic moment. We'll discuss it later. Okay, it is based on number of unpaired electron in d orbitals. Okay, this is the electronic arrangement representation in tabular form in the case of tetrahedral complex, right? You can calculate it easily. We have discussed earlier. These two are more popular complexes, but one more popular complex is there, that is this one, that is square planar, and we can discuss it to some extent. If in this case also this coordination number will be 4, and in this case 4 ligands are present in xy plane, that is ligand present in plane only, square planar. They are not present, if you compared it with the octahedral, they are not present at the z-axis. Okay, only x-axis and y-axis. These two ligands are present on x-axis, these are present on the y-axis. In this case, when ligand present along the x-axis and y-axis, the energy of orbitals of these two orbitals, that is orbitals involving x and y-axis, these are present, the lobes of these are present on the x-axis and y-axis, the lobes of these are present in between an xy, will be higher than these orbitals, that is dz square, okay, these xy, yz, right, xz and yz. These orbital having higher energy than these orbital involving this z component. Okay, as ligand are not present at the z axis, the orbital involving z component, that is these orbital, having less energy. Okay, because these lobes of orbital will be away from this ligand. And splitting of energy square planar can be represented in the term of del O only. This splitting can be represented in the term of del O. We can compare this splitting with del O, hypothetical del O. Okay. This is the representation. This is the orbital degenerated first state, right? It is the first state. That is the orbital, degenerated d orbital of free ion. This one is the degenerated d orbitals of the in the presence of ligand, spherical ligand field. This is the representation of octahedral splitting, which is hypothetical, and we can represent these orbitals, that is level of energy for square planar geometry in comparison to this octahedral splitting only. It is the just hypothetical splitting of octahedral complex, and we can calculate, we can represent it in the term of this del O, if this one is del O. Okay, then this G2G orbital having three type of the orbital, dxy, dyz and dxz, and xy orbitals goes to higher level than these two orbitals due to presence of this ligand in xy plane, and in this case dxy minus y square orbital will goes at the highest position, because these ligands are present on the x-axis and y-axis, and lobes of x square and y square present on the axis, and this z square goes to lower level because it has no component of this x or y. Okay, this is the representation. If it will be the barycenter, then it will be 0.23 del O, 1.23 del O. This is lower by, this is the difference between them. Barycenter, difference from barycenter, that is minus sign shows that lowering of energy, 0.43 and 0.51. This configuration is less important for exam point of view, but it is important. You should know that splitting will be different in this case, and electrons are filled according to energy of orbitals. Electron will go in this orbital, then this, and then this. Okay. And square planar geometry is most common in D8 metal, and in this case, this electron will present in this 4 electron present in lowest level of it, lowest orbital, energy orbital, that is the xy and dy, 2 electron will present in this orbital, 2 electron will present in this orbital. Square planar geometry of the D8 are the dimagnetic because this orbital having very high energy and no electron will present in this level, and all electrons are paired in this case. You can calculate CFSC also in the terms of del O. It is the number of electron in this orbitals. It is lowered by minus 0.51 del O plus 2 electron minus 0.43 del O plus it is this orbital is present above the barycenter. So these 2 electrons into 0.23 del O plus 1 pairing energy, it will give this one, that is CFSC can be calculated. You should know just splitting of square planar, but this splitting of octahedral complexes and tetrahedral complexes is more important. Then come to magnetic properties in the complex. As we have discussed spin only magnetic moment in the chart, the magnetic property of the complex, that is ligand present at the beginning of spectrochemical series are weak field ligand. We know that is the halide ligand, and the ligand present at the end of this series are called strong field ligand. The weak field ligand can give high spin complex, strong field ligand can give low spin complex. Okay, as we know, the paramagnetic behavior arises due to presence of unpaired electron in complex, and more unpaired electron, more paramagnetic behavior, and total magnetic moment can be considered as the sum of orbital magnetic moment plus magnetic moment due to spin of electron. Okay, you can represent in this way. This mu t, this is total magnetic moment. It is the sum of this orbital magnetic moment and spin magnetic moment. This equation shows that this total magnetic moment, where E is charge of the electron, V is C is the velocity of light, M is the mass of electron, and all that. This is the Planck constant. Okay. Then mu t can be represented as in this way. This is the Bm, that is called Bohr magneton. Okay. It is unit of magnetic moment, which is this one, and which value is 9.27 into 10 to power minus 21. You can represent this part in the form of Bm, this unit. Okay. In any complex, the orbital movement of electron is restricted due to presence of ligand, surrounding ligand. The ligand can restrict the orbital movement of the electron around the nucleus. As a result, the orbital contribution of magnetic moment, that is mu orbital, is negligible. Okay, and in that case mu s is important, that is mu s will be, that is mu spin will be important, that is mu effective will be is equal to mu spin, that is this one. This equation can be minimized in this way, and if this s is n by 2, okay, number of unpaired electron, if number of unpaired electron is n, then it will be n by 2 because each electron having a spin 1 by 2. Then you can calculate this mu spin by this equation, that is n plus 2 root Bm in the this unit, with this unit Bohr magneton, where n is unpaired electron. For example, this is a complex of cobalt with configuration D6. Unpaired electron will be 4 because it is this fluoride is weak field ligand. Then in the basis of this number of unpaired, you can calculate this mu s, and this in this way you can calculate this mu s value for each configuration. For example, in this case only one unpaired electron, this will be in this way. This is the 2 unpaired electron, this will this amount of mu s. This is the 3 unpaired. For 4 unpaired, this one, 5 unpaired, this one, this is for 4 unpaired, 3 unpaired, 2 unpaired, and 1 paired. We can calculate mu s value that is magnetic behavior, is paramagnetic or diamagnetic, to which extent it is paramagnetic, we can calculate by calculating this. Then come to next point and last point, that is color of the complex. Okay, the most of the transition metal complexes are colored as they can absorb in radiation, as they can absorb radiation in the visible region. The complex can absorb in the visible region, so that so these complexes give color. The color of complex depends upon transmitted light, not observed light. You know that it show complementary color. It means complementary color of the light absorbed, and it will show complementary color. If complex absorb red, then it will appear green. If it absorb orange, it will appear blue. It will absorb violet, it will appear yellow. And color is transition metal complex is due to excitation of electron in the d orbitals. It is due to dd transition, that is splitted d orbital. There is a difference between the energy of the splitted d orbital, and the transition between d orbital can cause can give color to the complex, can be reason of the color of the complex. Okay, the energy difference between the two sets of orbital, that is energy difference between two sets of orbital, that is del, is usually small. It is not very large, and electron can excite easily from one level to another, one lower level to another d orbital of the higher energy. And in octahedral complex, this can transfer from T2G to Eg. In tetrahedral complex, it can transfer from E to T2. Okay, as del depends upon the various factors, we know that the complex give different complex can give different color. For example, this is a complex having D1 arrangement, and this one electron will present in the T2G. We know that arrangement. This complex can absorb radiation, and this electron can jump from T2G to Eg orbital by absorbing radiation, and this radiation may be of wavelength this much, that is higher wavelength, and one electron jump from the T2G level to Eg level. Energy required for that, okay, and that energy can be calculated, that is E will be is equal to h nu, that is frequency, and Sc by lambda. This lambda, if lambda will be present, then this del can be calculated spectrophotochemically. Okay, this del O value or del T value for any complex can be calculated by this calculation. You can calculate this one. You can find this wavelength or frequency of radiation absorbed. Then you can calculate this E, that is difference between them. It will be is equal to del O. You can calculate it for different purpose. And in this case, it can absorb in green region and appear as purple. Okay. In the same way, if you compare these two compounds, these two complexes of the cobalt, in this case water is a ligand, in this case CN ligand, strong field ligand, in this case weak field ligand. Okay, and in this case del O will be small, in this case it will be large. In this case this energy required is small, in this case it will be large, and in this case the radiation of higher wavelength can be absorbed, in this case smaller wavelength absorbed, and color absorbed orange, in this case violet, it appears yellow and blue. They're complementary color. Okay. Thank you very much. Have a good day. We will discuss isomerism in next class. Okay.